So we have a solar collector of efficiency 80% and area of 20 meters square, receives 500 watt per meter square of incident solar energy per unit area. Knowing that the temperature of water entering the collector is 293 Kelvin, and the temperature of water leaving the collector is 333 Kelvin, calculate the time needed to heat 1,000 liters of water, knowing that the density of water is 1,000 kilogram per meter cube, and its specific heat is equal to 4 times 1,000 joule per kilogram Kelvin. Okay, so we talk about solar collectors last time, and we said that we work a lot on improving their efficiency to maximize the heat that can be extracted. And we can use them for several purposes. We can use them for domestic hot water needs, for underfloor heating, etc. So here is an application. So here we need to, it's a domestic hot water application. We need to heat water. We know that the inlet temperature of water entering the collector, Tn, is equal to 293 Kelvin. And T out is 333 Kelvin. So we have the value of delta T. And you know, whenever you have the temperature difference and you know the mass flow rate of water, how you can write the energy gained by water? Exactly. So Q gained is equal to M dot Cp. Of course, you don't have a change of phase because you are operating at a temperature above phase change of phase temperature. Since I gave you inlet to outlet different temperatures, so it's sensible heating. Okay, and you are away from 0 degrees, which is, and 100 degrees, which are the temperatures for water at which you have change of phase at standard conditions. Okay, so here we know for the water, we know Tn, we know T out, and we need to calculate the time needed to heat this volume for a volume of 1,000 liters, which corresponds to 1 meter cube. So to be able to find the time T, what do we need to calculate here? Yes, we need to calculate the time needed to heat this amount of water. Yes, M dot, okay, represent what? The mass flow rate in kilogram per second. It's equal to rho times Q, the volumetric rate. Okay, so if I get Q from energy balance, because what is Q gained? It's the heat gained from the solar collector. So if I do a heat transfer analysis, I can find what is Q. And once I find the Q, I say that this Q is equal to volume over time, V over T. Okay, so I need first to get Q. And once I get Q, to find the time needed, I just have to say that T is equal to the volume that I want to heat over the volumetric flow rate. Exactly. How can I get the total energy that I am extracting from the solar collector? They told me that my solar collector is characterized by an overall efficiency of 80%. And the area of my collector is 20 meters square. And this collector receives 500 watt per meter square. I get the energy transferred. Yani I have that this M dot Cp delta T is equal to what actually? It's equal to the efficiency of my collector times the maximum possible energy that I can take from my collector. What is the maximum possible energy that I can take? I have the area and I have the incident solar energy. So I have efficiency times area times incident energy, incident flux. Incident flux is the one that is perpendicular to my plate.
هي الفورمولا
Yes, if you have an inclination, you need to do projection. But here I directly gave you the incident value. Okay? So all you have to do is to multiply the efficiency by the incident solar energies. I call it in general G. Okay? Times, so A times G times the efficiency. And then you can say, once I do efficiency times A times G equals m dot Cp delta T, what is the only unknown in this equation? I have the efficiency is 80%, 0.8. The area is 20. The incident solar energy is 500. I have that Cp is given, Cp of water, 4 times 10 to the power 3. Okay, it should be in joule per kilogram Kelvin to have my result in meter cube per second. So pay attention for units. Okay. The unknown m dot. If since you have rho 1000, you get Q, the volumetric flow rate. هلا if you want ما تغلبته بين Q heat و volumetric flow rate, you can call it, you can put it V dot. في كتير بيسموها V dot. Okay, V dot, it's fine. So V dot is Q is equal to efficiency times area times incident solar energy over rho C delta T. Okay, just I pay attention for my units. I repeat, A meter square, G watt per meter square, rho kilogram per meter cube, C joule per kilogram Kelvin, T in Kelvin or degrees, it doesn't matter because it's delta T. Okay, so I get my volumetric flow rate in meter cube per second. Okay, and once I get the value of Q, I say the time is the volume over V dot. Okay, because look, what is the unit of Q? Meter cube per second, and volume is meter cube. So if you multiply Q by T, انتبه V هي الفوليوم meter cube, Q أو V dot هي meter cube per second. So when you multiply Q by T, you get the volume. So to get T, what should you do? Should divide the volume by V dot or Q. Okay. So this is for the first problem. Another problem. Assume that once. Yes, Rida.
Question بتاع wind problem 2.
Yes.
The second part where we reach the stream 2, turbine 2.
Yes, can we keep, Rida, can we keep this question for the end because it's on another chapter?
Okay.
So, problem 2. Assume that 1000 watt per meter square of solar radiation is incident on a solar panel of 1 meter square that converts 10% of the energy to electricity. 10% is really small, okay? That's why when we worked on PV systems, we tried a lot to enhance their efficiency, electrical efficiency, plus we introduced heat recovery. Because if you use heat recovery, you can increase a lot the overall efficiency of your system, okay? So assume that a heat transfer coefficient of 12 watt per meter square Kelvin is effective on both sides of the panel. What do we mean by this? So you have a panel, okay?
Heat transfer coefficient HH.
Heat transfer coefficient HH. This panel is exposed to air from the upper side and from lower side. In general, lower side we insulate. We do insulation to reduce losses, okay? But in case we don't have insulation, we can use heat recovery, okay? Because here, the purpose here of this panel is not to heat water, is to have electrical. The main purpose was to create electricity. But since we have only 10% of efficiency for electricity, 10% of this energy will be converted to electricity. To not lose the remaining part, what we will do is the following. For the upper, for convection from upper side, we cannot benefit from it because we need, if you want, we need the solar energy to strike the solar panel. So can we put any obstacle or can we move water from the upper side? No. Okay. So from the upper side, heat will be lost. We can't do anything. But from the side at the back, in order to profit from this released energy, we can pass, for example, tubes of water from the lower side, okay? And then extract the heat that is rejected. So this is heat recovery. Or sometimes what we do, we insulate. We put insulation in order to convert, in case the main purpose was not to produce electricity. If the main purpose is to have heating, then we insulate the backward side. And within the collector, and just after the class, what do we put? We put the tubes to directly extract the energy. We'll see it in another application. But if the purpose is to generate electricity, so you have the upper, as we said, for the upper part, you cannot put any obstacle. For the lower part, you can have any heat exchangers that you can put any type of heat exchangers there in order to extract the heat that is lost by convection. Okay. So in the first questions, I said, what will be the efficiency of the combined system? If we just consider electrical efficiency, what should we do? They already gave us the electrical efficiency. It's only 10%. But if we profit from heat from backside, what will be the overall efficiency? And overall, it will be equal to the electrical power, okay, plus what? Recovered heat over total energy incident, okay, over total incident. So here they told us, what is the incident total energy? 1000. So here we replace the total by 1000 watt per meter square. Okay. Now, 10% is electrical. So what is the amount of electricity? So we just multiply 1000 by 10%. It's 100 watt. So 100 watt of electricity. Now, the reflected part, okay, they said that what is the absorbed part? We have 10% reflected and 90% absorbed. So you have that also 100% will be rejected, and I will lose it. Okay. Then the remaining part is 800. This part will be, this is, because you are operating in steady state, sum n equal to sum out. So this part will be convected from, due to symmetry, it will be convected equally from the upper and lower side. So if this is your collector, you will have from the upper side HA delta T. Okay. And also from the lower side, you have HA delta T. You have the convective coefficient is 12. So you have 12 times. Here, if you want, since we are doing the analysis for 1 meter square, we just multiply by 1. Okay. And delta T is what? 53 minus 20. So if you do the calculation, you obtain that heat lost from upper and lower side is equal to 400. That's why here, if you want, they didn't give us the reflected part because we can deduce it. Okay. Because you know what is H, you know delta T. So when you do H delta T, HA delta T, you get the power of convection. And then because of steady state conditions, to get what is the reflected part, you just say I have 1000, which is incident, okay, will be divided into one part that is reflected and 2 parts that are convected, okay? So now to profit from heat, we can only profit from the backward side because at the upper side, I cannot do anything. I have the incident flux, okay? So if I want to profit, I should use heat recovery. If I am able to use heat I can recover completely heat from the backward side. What is the maximum efficiency I can reach? So I should add the electrical power, which is 100, plus the backward, the heat recovered from backward side, which is 400 over 1000. So I can reach an efficiency up to 50%. So from here, the importance of heat recovery. Yani my system, if I just use it for electrical generation, it's only 10% efficient. While if I use it, if I use a combined system with heat recovery, I can reach up to 50% efficiency. Okay. Another problem. Consider a solar flux of 700 watt per meter square that is incident on a flat plate solar collector used to heat water. The area of the collector is 3 meters square, and 90% of the solar radiation passes through the cover glass and is absorbed by the absorber plate. The remaining 10% is reflected away from the collector, and water flows through the tube passages on the back side of the absorber plate and is heated from an inlet temperature T inner to an outlet temperature T out. The cover glass is operating at a temperature of 30 degrees. It has an emissivity of 0.94 and experiences radiation exchange with the sky at -10 degrees. The convection coefficient between the cover glass and the ambient air at 25 degrees is 10 watt per meter square Kelvin. Okay. And I need to find first what is the value of useful heat and what is the efficiency of the solar collector. Okay. So let us do the analysis of our collector. What is happening? So what is the difference between this collector and the other one? The other one, the purpose of the other one was mainly to produce electricity. And we said that we can use heat recovery from the backward side. While this collector has a purpose just to heat water. In here, we just have the useful heat is the heat extracted by water. Okay? Now, what will happen actually? So first, this is my solar panel. Okay? If I take as control volume, if you want, just this system, okay? This part of my system. I have heat exchange between this part and the water in the ducts, okay? So if I want to do the analysis to know what is the useful heat that is given to water, I need to know what are the different fluxes for this part of my solar system. So here you have a glass panel, okay? The glass cover will receive the solar radiation, okay? And we have the value of solar radiation. But we know that the part that will enter is absorbed, it's alpha times G, okay? And we know in this problem, they gave us the amount of energy of radiation that will pass through my glass cover and will be absorbed by the plate. While the remaining part, 10%, will be reflected. And for me, what will enter my system is just what? Alpha times the solar flux. Okay? Now, since the temperature of my glass cover is relatively high, it will lose heat to the surrounding by both convection and radiation. And we know already that what is the convective flux? H, if I do the analysis per meter square, it's H times delta T, which is, what is delta T here? The temperature at surface of my panel minus what? Minus T surrounding, very good. Minus T infinity, okay? And I have T infinity is given 25 degrees, and the convective coefficient with surrounding is also given. So I can calculate the heat transfer by convection. Now for radiation flux, okay, what is the expression? Epsilon. This is the emitted flux, okay? It's epsilon sigma. They told me, assume you have radiation with the sky. And they gave me the temperature of the sky. So I should use epsilon sigma T surface of the panel to the power 4 minus T sky. And I should not forget that these temperatures are in which unit? In Kelvin. Okay. For convection, for delta T, you can put it in Kelvin or degrees. It doesn't matter. But for radiation, it should be in Kelvin. Okay.
Why do solar is equal to 0.9 US?
Because alpha is the absorption part. 10% will be reflected. Will not enter your system. And whenever you have an incident flux. No?
US is the system. US
QS is, yes, you are doing the analysis for your solar system. Your solar system will receive solar radiation. 90% of it. 10% will be reflected and it will not enter the system. So that's why we don't account for it. Okay?
لو كان 100% يعني يكون لك solar
كله. Exactly. But here you are, as I told you, that you can only absorb 90% of this energy. Okay? So now, what is my only unknown here? The useful heat that I can extract from my solar collector. Because if I work in steady state operation, what can I say? Sum of E dot N equals to what? Sum of E dot out. So what are my inlets here? The only inlet is the solar radiation in, okay? But I have losses, E dot out are Q radiation, Q second radiation, Q second convection, and Q second that will be transferred to water. Okay? So we can say that this is what I want. I want to try to increase this as much as possible. This is the useful energy that I can extract from my solar collector. So this is in watt per meter square. If I want to have it in watt, I just have to multiply by the area. So if I do Q second useful times the area of my collector, what do I get? It should be equal to what? This useful heat is used to do what? To heat water. So it's equal to m dot Cp times delta T. And in this problem, they are asking me to find the value of delta T. Okay. So let us go again through the procedure of solving.
Just one question. Will you give us these germane?
Here, yes, because it's a complex system. I give you the drawing. If it's complex, yes. If not, no. Okay. Okay. So as we said, first we define the collector as the control volume and we write the energy balance. And because we are working in steady state case and no storage within the collector, okay, then we can say that sum of E dot N equals to sum of E dot out. So we have Q dot solar, Q second solar is coming in, so plus, and we have three outlets, so minus Q second radiation, minus Q second convection, minus Q second useful, because I'm losing these parts. Okay, now from here I can calculate the useful heat that will be given to my water. So this is what I care for. I want to determine what is the useful heat that will leave the collector and go to water. Okay, so I can, as we said, the incident flux is 90% times the solar flux. For radiation, it's epsilon sigma T surface of glass to the power 4 minus T sky to the power 4 minus H times T surface minus T infinity. Then I can calculate the useful flux in watt per meter square. And once I obtain this useful flux will be transferred to water to increase its temperature. So it's so Q second times area of the collector is equal to m dot Cp delta T. Now, if I ask you to find what is the efficiency of your solar collector, how you can calculate the overall efficiency? What is the overall efficiency here? Whenever I tell you to define an efficiency, you put useful over input. What was your input here? So, إذا عم بحكي overall efficiency, you take G. يعني what was the incident solar flux? G. What was the amount that I was able to extract? Q second useful. So the efficiency, the overall efficiency of my system can be calculated as Q second useful over Q second solar.
ما بناخد radiation.
لأنه already هول losses. نحن why we talk about overall efficiency? يعني we consider all losses, the reflected part, will part lost by convection and radiation. Okay, so the overall efficiency of our system is useful over the maximum energy, which is the solar incident energy. So we have an efficiency of 60%, which is a good efficiency. Okay, actually, we still have possibility of losing heat by what? You know, if you have for water, if you don't insulate well your heat exchanger, you can have losses to the outer environment. So we can have additional losses if we don't have perfect insulation from the others. Okay.
هون في شيء مثل turbine بتكفي 99% أو parasite efficiency.
No, هون ما في you don't have this upper limit condition. No.
في lower.
No, you don't have. So it depends on the system. You can optimize. You optimize first the orientation of your system to increase the incident angle, because as your friend said, if you don't have a good inclination, we'll have to project, to have the perpendicular, and you need to do times cosine and angle. So you need to orient your solar collector in a way to maximize the absorption. Okay. You need also, once again, you need also to insulate the backward side of your heat exchanger to not have losses to the external environment. So you have a lot of possibility of losses. If you tackle them, you can increase the efficiency of your system. Yes.
كيف صارت QS 800 مش QS is equal to Q solar of 0.9 شيء هون 700
No, this is a typing error بالgiven. It's 800.
اوكي
بس 90% انت مزبوط هي 90% تجيب الابسورب. بس انت when you calculate the overall efficiency, you put the useful over the maximum possible that you can extract. اللي هي 800. اوكي؟ يعني انت reflectivity هي
انا استعملت 90%
تطلع الكيو ان. يعني انا كيو لا اوكي اسمع، انت عندك كيو يلي اجى لعندك الانسيدنت is 800. هيدا الماكسيمم possible that you can take، صح؟
انا استعملت منه 90%.
اول شيء استعملت منه 90% تفت لجوا، بس من بعد ما فات لجوا رجع طلع part by radiation and by اكثر 10% هي reflected. يعني انت اذا if I want to divide things, first you have an incident flux of 800. okay, you have one part that is reflected. يعني 10%، يعني 80 is reflected خسرناها. We lost this part. So what was the part absorbed? 0.9 times 800. هلا this absorbed part is divided into 3 flux. One that will go to water, and this is the useful, Q second useful. But since you have the temperature of your glass is larger than temperature of surrounding, you will have losses by both convection and radiation. So these also are losses. And at the end, what is the maximum possible value you can get? 800. What is it?
efficiency استعمل 800 maximum.
Yes, I use useful over max. Okay. Other question on this problem? Okay, great.